So now that we have infinite series around, what we need to figure out is a way to check whether they converge or not. We saw in the last set of lectures that there's a few situations in which we can get lucky and we can actually find out the sum of an infinite series. We can find out whether it converges or not. All right? Sometimes we can find the pattern in the partial sums. If it's a geometric series, we just have to know, is the absolute value of the ratio less than 1 or not? Right? But generally speaking, a series isn't going to be a geometric series. That's a pretty special thing. And, more likely than not, we're not going to be able to, at least easily, find a pattern for partial sums. So, what we do have is sort of a series of tests to try and figure out, well, when does a series converge, when does it diverge? So we're going to talk about 3 of those in this group of lectures, and then we'll add in one more called the ratio test. So let's start with the divergence test. So the divergence test is by far the simplest test, and because it's the simplest test, it actually doesn't tell us anything about whether a series converges. It only says whether a series diverges, hence the divergence test. So, well, what is this? Right? So, the simplest way to state the theorem is that if an infinite series converges, so here you'll notice I just have sum of AK. I didn't put any bounds on it because it doesn't matter what K value it starts at. As long as it goes off to infinity, it doesn't matter either way. Right? But if that sum converges, then the limit of the terms has to go to 0. If we take what's called the logical contrapositive of that statement, which just means another statement that's equivalent to it, what we can say then is, if the limit of the terms of the things we're adding up is not 0, then the series has to diverge, right? Because, and this works out because we know if the series converges, then the limit must be 0. So therefore, if the limit's not 0, then the series can't be convergent. So what is the reasoning behind this? So let me switch back over here. The reasoning behind this test here is as follows, right? If we're not adding up smaller and smaller things every time, so let's say we pick something simple here. Let's say, for the series of AKs, let's say we have that the limit as k goes to infinity of these things. Let's say it's L, whatever L happens to be, right? And let's say that value L is right here, right? Let me just draw a red line here, right? If that limit, if the limit of the things that we're adding up is L, what that means is, these first few terms, AK, they can be sort of all over the place. There's no real sort of rhyme or reason that they have to obey. When it comes to an infinite series, it really matters what we're doing in sort of the tail, so to speak, of the series, which is the, past a certain point, we need to add up basically 0. So, at some point here, these terms have to get closer and closer, right? If it's a sequence that's converging to L, these dots have to eventually kind of settle down on L there. So what does that mean is kind of happening? Well, if these values are approaching L, then at some point, this sum for, let's say, somewhere around, let's say this is capital N right here, right? After, say, this point in the sequence, everything here is really close to L. What we're essentially doing there, then, is saying, all right, well, from k equals n to infinity, this series basically looks like L plus L plus L plus L plus L plus L. You get the point here. We just keep adding up L over and over. And again, that's because in order for this sequence to converge, these values, these dots, have to get closer and closer to L. Remember, this is the same thing what it means for a limit to exist, right? The function has to get really close to that value. So we're approximately just adding an L for each point here now, but there's infinitely many of these, so this has to diverge. All right. So because of that is why if the limit is not 0, then the series must diverge. So let's look at some examples. I won't switch back over to the Mathematica slide, but this will be posted as usual. Right, so let's use the divergence test on some examples here. Right? For example, let's say we have the series from 0 to infinity of k over 2k plus 3. Right? So is this convergent, or sorry, does this diverge or does the test fail? Is the test inconclusive? Right? So here, our AK is k over 2k plus 3. Right? And then the limit as k goes to infinity of AK is the limit as k goes to infinity of k over 2k plus 3. Right? And, think back to how we compute limits. We know this is 1/2. And so this means the series diverges. Right? The divergence test says that since this limit is not 0, this series must diverge. All right, let's look at another example here. 2. K equals 0 to infinity of k over k squared plus 1. Right? Let's look at this. So again, here, this is our AK right here. So we're asking, what is the value of this limit? Right? As k goes to infinity of k over k squared plus 1. Right? Again, reach back and think about how to compute limits. And you'll remember, since the degree on the bottom is higher, this limit has to be 0. Right? So here, the test is inconclusive. Right? So I'll let you think about, whether you think that series should actually converge or not. Let's do one more example, just to finish this off here. This is a bit of a simpler one, but it's an important example. All right, let's just look at the pretty simple series here. Actually, this should really start at k equals 1. So k equals 1 to infinity of 1 over k. All right, the question is, does this converge or diverge? Well, if we take the limit as k goes to infinity of 1 over k, we get 0. So again, inconclusive test. Right? I really, really want to emphasize here that this simple test can only test whether a series diverges. Right? If we get a limit of 0, the series might still diverge. But if we ever get a limit that is not 0, the test 100% for sure tells us that the series must diverge.